Dear students, greetings for the day. In the previous class, we discussed the derivation of ideal gas equation and value of universal gas constant and learn about the isothermal process and adiabatic process and differences between isothermal process and adiabatic process. Now in this class, we shall discuss in detail about the laws of thermodynamics, specific heats of the gas and relation between the specific heats of the gas. So here there are two laws of thermodynamics. First law of thermodynamics states that about the law of conservation of energy. So according to first law of thermodynamics, the heat energy supplied to the system is equal to the increase in internal energy and external work done by the system. So when we supply some heat energy to the system or gas, then it is utilized, some of the supplied energy is utilized to increase the internal energy, that is to increase the temperature, and the remaining amount of energy is utilized to do some work during the expansion of the gas. So first law of thermodynamics states that the heat energy supplied to the system here system means gas. Equal to the slope. Therefore, from first law, let the dq be the energy supplied. Du be the increase in internal energy. And maybe external work done by the system, then according to first law of thermodynamics, dq is equal to du plus dw. This is known as a mathematical form of the first law of thermodynamics. So here heat energy supplied to the system is dq and the increase in internal energy is du. It is equal to the sum of increase in internal energy and this external work done by the gas. So this is nothing but increase in temperature dt plus work done by the system. It is P into V2 minus V1 during expansion when at constant temperature, at constant pressure. If the volume rises from V1 to V2, when temperature rises from T1 to T2, then external work done by the gas is PV2 minus PV1. Now we shall discuss about the applications of first law. Now we discuss about the application of first law of thermodynamics to the isothermal process. In isothermal process, temperature is constant. Therefore, internal energy remains same. That is, increase in internal energy is 0. So du is equal to 0. Therefore, heat energy supplied to the system is utilized to expansion of the gas, that is some work is done. Therefore dq is equal to dw. So as temperature is constant, internal energy remains constant. Therefore du is equal to dt equal to 0. Therefore here, therefore dq is equal to du plus dw. dq is equal to 0 plus dw. That is dq is equal to dw. So here the supplied heat energy is entirely utilized to do some work during the expansion of the gas. Therefore dq is equal to dw. During compression it is equal to negative work minus dw. Now application of thermodynamics to adiabatic process. So in this process, let us supply energy to the system at constant pressure. Then it is also known as isobaric process. So here temperature is increased from T1 to T2. Therefore internal energy also increases. and remaining part part of the supplied energy is utilized to do some work. Therefore, here dq is equal to dq plus dw. So sum of the energy supplied energy is utilized to increase in internal energy, and the remaining part is utilized to do some work. And isochoric process volume remains constant. When we apply to isochoric process, here as volume remains constant, here dq is equal to pdv. So entire supplied heat energy the entire supplied heat energy is utilized to increase the temperature and hence internal energy. Therefore, dq is equal to du or dt in this case, and dw is equal to 0. As the volume constant, there is no displacement. dw equal to 0. Therefore, dq is equal to du or dt. Now, we discuss the second law of thermodynamics. It states that we know that water always flows from higher level to lower level. Similarly, heat energy flows from a body at higher temperature to a body at a lower temperature. This is generally happens, but under the influence of external agency, heat energy flows from your body at lower temperature to your body at a higher temperature in the reverse process, like water through using motor sending from ground to water tank. So second law of thermodynamics states that it is impossible to transfer heat energy from a body at lower temperature to a body at higher temperature unless there is the aid of external agency like refrigerating machine. So it states that heat energy flows from a body at lower temperature to a body at higher temperature. Only with the help of external agency. Like refrigerating machine. So, according to second law of thermodynamics, the heat energy flows from a body at lower temperature to a body at a higher temperature only with the help of external agency like AC or refrigerating machine. Examples of first law of thermodynamics are the explosion of a firecracker in an insulated steel drum. First law applications in heat, diesel, petrol engines are also there. And first law tells about the conversion of mechanical energy into heat. And first law is used to calculate the increase in internal energy in the process like boiling and melting. And second law of thermodynamics examples are working of the principle of refrigerator, working of water coolers, working of cold storage units and AC units. Like solids, gases also has specific heat. In the case of solids, specific heat of a solid is the nothing but the amount of heat energy supplied to the substance to increase the temperature of a given mass of gas through T degree centigrade. Through 1 degree centigrade. So specific heat of a substance is nothing but the amount of heat energy supplied to the substance of a given mass of gas to increase its temperature by through 1 degree centigrade. heat supplied dq is proportional to mass of the substance m, and it is dq is proportional to temperature difference T2 minus T1. Therefore, dq is proportional in the case of solids. dq is proportional to, therefore by combining dq is proportional to m into T2 minus T1, or dq is equal to proportionality constant C or S. We shall write C into m into delta T. The temperature difference is delta T. Or sometimes it may be written as S into m into dt also. So ms dt. So in the case of solids, here proportionality constant is called specific heat of the given solid, SRC. In the case of gases, as the gas possesses at particular temperature, it possesses both pressure and volume. So with the rise in temperature, its pressure increases and volume increases. So gases possess two types of specific heat constants. So in the case of gas, if we similarly in the case of gas, here constant is CRS is, in the case of constant pressure, this constant is named as Cp, or at constant volume Cv into m into dt. Therefore, there are two specific heats of a gas. First one, specific heat of a at constant pressure. It is represented by Cp. And the second one, specific heat of a gas at constant volume. It is represented by Cv. So specific heat of a gas at constant pressure is defined as the amount of heat energy required to raise the temperature of a given mass of gas through 1 degree Kelvin or 1 degree centigrade. In a system, 1 degree Kelvin. And specific heat of a gas at constant volume is the heat energy required by the gas at constant volume. That is the heat energy supplied to the gas to raise its temperature by 1 degree Kelvin at constant volume. So specific heat of a gas at constant volume is defined as the heat energy required to raise the temperature of unit mass of gas through 1 degree Kelvin. So when it is unit mass, then m is equal to 1. Therefore, Cp is equal to 1 unit mass. Then here m is equal to 1. Therefore, Cp is equal to dq by dt. And when the heat energy supplied to the system at constant volume, its entire energy supplied is utilized to increase temperature, so that internal energy increases. Therefore, here in the case of dq, this dq is equal to the internal energy. dq is equal to Cv into dt. From this case, Cv can be written as du by, so heat energy dq is equal to du, in this case dt. But to increase the temperature for through 1 degree Kelvin, the entire energy supplied is utilized to increase the temperature, so its internal energy increases. But in the case of constant pressure, here the specific heat of a gas at constant pressure is utilized to increase in temperature and also increase it to do some part is utilized to increase the internal energy. Therefore, Cp is greater than Cv. Now we discuss about molar specific heat. Molar specific heat of a gas at a constant pressure. And the molar specific heat of a gas at constant volume. It is denoted by mCp. If we consider 1 gram molecule of gas, then its molar weight is capital M. Therefore, specific heat into molar weight here, mCp. Therefore, molar specific heat of a gas at constant pressure is defined as the amount of heat energy required to raise the temperature of 1 gram molecule of gas through 1 degree Kelvin. Similarly, molar specific heat of a gas at constant volume is defined as the heat energy required to raise the heat energy supplied to the system to increase the temperature of 1 gram molecule of gas through 1 degree Kelvin. So here it is mCp. So mCp is equal to m into Cv. Generally it is represented by capital letter Cp. Here small letters here Cp. Cp is also equal to same. Generally when we consider it, we use these expressions only. Cp for this, Cv for this. Same expressions we use generally. So in the case of molar specific heats, we use 1 gram molecule of the gas. Now let us derive the relation between Cp and Cv. Cp is greater than Cv because the energy required to raise the temperature of the 1 gram molecule of gas through 1 degree Kelvin at constant volume is less than the molar specific heat of a gas at constant pressure Cp, because the amount of heat energy in this case required dq is more than du. That is, here dq is utilized to do increase in some part is utilized to increase the temperature and hence the internal energy, and the remaining part is utilized to do some work in this case. Now let us derive the relation between the Cp and Cv, two specific heats of the gas. This relation is Cp minus Cv equal to R, capital R, that is universal gas constant, and it is known as Mayer's equation. So let us derive Mayer's equation. Cp and Cv, that is Mayer's equation. It is known as Mayer's equation. So in this derivation, let us consider 1 gram molecule of gas which is enclosed in a non-conducting vessel or non-conducting cylinder. Let the initial volume be V1 at a temperature T1. Now, if we keep the temperature changing from T1 to T2, that its volume increases from V1 to V2. Right. So here V1 and the total part is V2. So when we supply some heat energy, so at constant pressure, then this is increasing volume. So here when temperature of the gas increases and some force is acting on the piston. So we know that force on the piston, consider 1 gram mole of a ideal gas. Enclosed in a non-conducting cylinder having piston of air gap A. Here A equal to L into B or pi r square. If it is circular one, area of the piston be pi r square. Now, if we supply some heat energy dq, then at constant pressure, then the gas is allowed to expand. So some force is acting on the piston, and force on the piston is given by pressure into area of the piston. So P into A. Here F is equal to P into A. Force on the piston is P into A. So when the temperature of the gas rises through 1 degree centigrade, that is T2 is equal to T1 plus 1, then that its volume increases from V1 to V2. Therefore, increase in volume dV is equal to V2 minus V1. And temperature also increases through 1 degree centigrade from T1 to T2. Therefore, here displacement let it be S equal to dx. Therefore, work done by the system during expansion work done by the gas during expansion, work done by the system, F into S, that is P into A into dx, S equal to. So area into here, volume, pressure into increase in volume, nothing but Therefore, work done by the system dW is equal to pressure into increase in volume. Therefore, P into dV. This is the expression for external work done by the gas. Now, according to first law of thermodynamics, from first law of thermodynamics, heat energy supplied to the system is equal to du plus dW. So, when the gas is heated, that is amount of heat energy supplied under isothermal conditions, the entire energy is utilized to increase the temperature and hence increase in internal energy. So at constant temperature, at constant pressure, or at constant volume. There are two cases. First one we consider at constant volume. So in this case, dW is equal to, there is no displacement, therefore dQ is equal to du. But from the definition of specific heat at constant volume, the amount of heat energy supplied to the system at constant volume is denoted by Cv, and it is equal to dQ by dt. Already definitions. And at constant pressure, and we supply heat energy dQ at constant pressure. So at constant volume, the heat energy supplied to increase 1 degree centigrade or 1 degree Kelvin, then it is equal to dQ is equal to du. Therefore, Cv is equal to du by dt. It is equal to internal energy at constant pressure. So to raise the temperature through 1 degree Kelvin at constant pressure, sum of supplied energy is utilized to increase the temperature through 1 degree centigrade, and the remaining part is used to expansion of the gas. Therefore, dQ is equal to du plus dW in this case. So here dQ is equal to du, its value is more. Therefore, dQ is equal to du, and it is equal to Cp. From the definition, the heat energy supplied to the gas at constant pressure is called, dQ is called Cp, specific heat at constant pressure. Therefore, it is equal to dQ by dt. So from these expressions, du is equal to Cv dt, and from this expression dQ is equal to Cp dt. So let this be 1, let this be 2, let this be 3. So by substituting the values of dW, dQ and du values from 1 to 3 equations, we get here dq is equal to cp into dt, and this is du is equal to cv into dt plus dw. Now we know that ideal gas equation, from ideal gas equation, when we here at constant pressure, if temperature increases, volume increases. Therefore, some work is done during expansion. Therefore, here PdV is equal to R into dt, or P into V2 minus V1 is equal to R into T2 minus T1. Therefore, when temperature rises from T1 to T2, then at constant pressure, volume increased by V2 minus V1. Therefore, pressure into change in volume nothing but dW may be written as R dt. Therefore, let this be 5. By substituting the value of 5 in 4, Cp dt is equal to Cv dt plus R dt. So, by dividing with dt on both sides, we get Cp is equal to Cv plus R, or Cp minus Cv is equal to R. This is known as Mayer's equation. This is the relation between Cp and Cv, and difference between Cp and Cv is equal to universal gas constant. This is known as Mayer's equation. This is also known as Mayer's equation. So here we consider the 1 gram molecule of gas which is having volume V1 at initial temperature T1 degrees Kelvin, which is enclosed in non-conducting vessel. So here, when some energy is supplied at constant pressure, then it's first let us assume that its temperature increased by through 1 degree Kelvin. Then the entire energy supplied is utilized to do the increase in internal energy or increase in temperature. Therefore, dq is equal to Cv dt, or it is equal to du. Therefore, du is equal to Cv dt, or from definition Cv specified at constant volume, Cv equal to du by dt, du is equal to Cv dt. And after that, keeping the pressure constant, the gas is allowed to expand during the rise of temperature through 1 degree Kelvin. Let the gas expands from volume V1 to V2 volume. Therefore, increase in volume is dV, or V2 minus V1. So, in this case, as there is the displacement of the piston and force on the piston, some work is done by the gas, and it is equal to dW. And this dW is equal to, from gas equation, dW equal to RdT, and as the entire energy is supplied to the system is dQ, which is more than Cv. So at constant pressure the energy supplied is called specific heat of the gas at constant pressure Cp, which is equal to Cp equal to dQ by dt, or dQ is equal to Cp dt. So by substituting the values here, as per first law, dQ is equal to du plus dw. dQ value is Cp dt, du value is Cv dt, from 1, 2 and 3 equations. From 4th to 5th equation here, dw was equal to RdT. Therefore substituting these values in 4, we get equation like this. Dividing with dt on both sides, we get Cp equal to Cv plus R, or Cp minus Cv equal to capital R, universal gas constant, it is equal to. And the ratio between specific heats of the gas Cp by Cv equal to gamma, it is equal to gas constant. So let us conclude this class, and the heat and thermodynamics is completed. In the next class we shall do some problems on isothermal process and on this relation between specific heats of the gas. Thank you.